Assalamu alaikum dear students. Today we are starting a new topic under the heading of quantum number. So as you can see, it's a number, and quantum also represents any number. It's like any number from 0 to onwards. Now, what are quantum numbers? There are 4 quantum numbers which describe the electron in an atom. They are denoted by the letters N, L, M, and S, called the principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number respective. Now, in order to identify the exact position of electron in the atom, you have to understand these quantum numbers. Now, in order to get the exact location of a person, you need to know the exact address for that person. Like, for example, if you want to go to someone's house, you must know that the address is, say, R124, sector 14B, Shadman Town, Lahore. So these numbers are actually denoting the exact location of that house. Similarly, if you want to know the exact position of electron in an atom, you need to understand these numbers like principal quantum number, azimuthal, magnetic, and spin quantum number. Now let's try to understand what is principal quantum number. This quantum number describes the motion of an electron in an orbit or the shell which is present in an atom. In other words, it is a rough measure of the size of the orbit. The larger the value of n, the greater is the volume or bulk of the electronic density. N may have any integral value, that is from 1 till 7. Like we have 7 periods in the periodic table, 7 rows. If you remember, yesterday we learned about the periodic table, that there are 7 periods, horizontal rows in the periodic table. So it can go from, this principal quantum number can go from 1 till 7. The value of n describes the binding force and distance between the nucleus and the orbit in which an electron moves. It also tells you the binding force or the force of attraction between the nucleus and the orbit in which the electron is present. The lower the value, the lower is the energy. Like if n's value is 1, it has the lowest energy level, and if it has 7 or 5, it has the higher energy levels, while the higher value of n corresponds to the highest energy levels. The energy levels K, L, M, N, O, P, and Q corresponds to n is equals to 1, 2, 3. Like if the value of n is equals to 1, it will be K shell, K energy level. If it's 2, it will be L. If it's 3, it will be M. So and vice versa accordingly if you go. So it will be like this. The value of n also determines the number of breaks and discontinuities in the electronic cloud. These breaks are also called nodes. The number of breaks is given by n-1 and is denoted by L, called azimuthal quantum number. Now these energy levels or the electrons presence in these shell is not continuous. There are some breaks in there, and how those breaks are explained, it is explained by another quantum number that is called azimuthal quantum number. So let's see this principal quantum number here. Now this is your nucleus, and these are the energy levels, or you sometimes you call it the shells. This is the first shell, second, third, fourth, and up till 7 it goes. So you can see if n is equals to 1, it's K shell. If n is equals to 2, it's L shell or energy level. So this is the principal quantum number. That's it. Now let's try to understand what is azimuthal quantum number. This quantum number describes the shape of an orbit. Its value corresponds to the value of n and is given by n-1. So basically the azimuthal quantum number, what it tells you, the shape of the orbit, like where the electron presence, like if it is in the K shell, but in K shell, where is the exact position? Like, is it present in a spherical form or in a dumbbell form? So how is it present? Like, what is the exact shape of the orbit? The azimuthal quantum number tells you that. Its value corresponds to the value of n, and this azimuthal quantum number depends on the value of n, like it depends on the principal quantum number. And how can we calculate that? By subtracting the value of principal quantum number by 1. It is also called secondary quantum number. The value of L tells whether the orbit is spherical, like whether the orbital is circular in shape, is like a dumbbell, sausage shaped, or even more complicated. Like the value of azimuthal quantum number basically tells you the shape of the orbit where the electron is present. It means that L is associated with a certain value of an angular momentum. The larger the value of L, the more complicated will be the shape of the electronic cloud. The angular momentum is given by this formula. mvr is equals to h upon 2 pi, and you have taken the square root of azimuthal quantum number, and this value is here. This quantum number explains the fine structural lines in the spectra. When you must have seen the hydrogen spectra, and there are some fine lines in the hydrogen spectra, and those lines are basically explained by azimuthal quantum number, that electron is not present in one particular place. It is present in the orbits, and those orbits can be of spherical shape, it can be of dumbbell shaped, it can be of sausage shape, or it can also be more complicated shapes. So the resolution of single line into two or more than two lines indicates that there are various sublevels in an energy levels in which an electron revolves. The energy is also quantized in various subshells or sublevels. The main energy shell thus can be considered as being made up of one or more energy sublevels. According to Sommerfeld modification, the electrons in any particular energy level could either have a circular orbit or a number of elliptical orbitals about the nucleus. And if you can see here, this is the azimuthal quantum number. Like the shape of the orbital can be spherical, can be dumbbell, can be sausage shape, or more complicated. Now if L, like if the energy level you subtracted it with 1, so the L value will come 0 and the orbital shape will be spherical. If L comes 1, the shape of the orbital is P, and this is, you can see here, this is the dumbbell shape. And for d orbitals, it's like this. And for f orbitals, it's more complicated. And here you can see this is the spherical, and for p orbital there are different orientations. For d orbital, these are the different orientations, and for c or of f orbitals, these are the different orientations. Okay, so let's understand what is the magnetic quantum number. Now this quantum number explains the magnetic properties of an electron. The motion of an electron around a nucleus produces a magnetic field. Now when the electron moves in an atom, it produces its own magnetic field, now which can be presented as a vector in the direction of an external applied field. This vector is 0 for an s orbital because of its spherical symmetry. When there are more than one orbital of a given type, these cannot possibly all line up equally with an external magnetic field. This difference in orientation is represented by a magnetic quantum number m, which may have values from 0 to plus minus L as shown in the figure 1.6. We will figure out what is this 1.6. In the above figure, the splitting of the spectral lines are shown for L is equals to, when L azimuthal quantum number is equals to 1 and the orbital is p orbital, and when azimuthal quantum number is equals to 2, it's showing the splitting as d orbital here. You can see this is for p. If L is equals to 0, there will be no magnetic or zero quantum number. There will be no like magnetic field will not be generated. But if L is equals to 1, you can see here it can be plus 1, 0 and minus 1. If L is equals to 2, so there will be this splitting here from plus 2, plus 1, then 0, minus 1, and in total there are 5 values or 5 sub-levels. And if L is equals to 3, you can see 1 from plus 3 till minus 3 you have to go, and there are total 1, 2, 3, 4, 5, 6, 7 suborbitals. So here you can see for magnetic quantum number, if S is here, then magnetic quantum number will be 0. If it is in p orbital, the magnetic quantum number can be from minus 1 till plus 1, like we have 3 orbitals. If it's in d orbital, there are possibilities of having like 1, 2, 3, 4 and 5 suborbitals. If it is in f orbital, the possibilities are like minus 3, minus 2, minus 1, like the 7 suborbitals. With different orientation in space, the arrows indicate an appropriate quantum number, that is the value of m. The angular momentum in the direction of the applied field is given by angular momentum is equals to mLh divided by 2 pi. The values of m are given in table 1.5. It is clear from the table that when n is equals to 1, L will be equals to 0, as we know that the value of L is equals to n minus 1. So when n is equals to 1, so if you subtract it, L will be 0 and this will be s orbital. And the value of magnetic quantum number will also be 0. Hence the number of orbital is 1, which is circular and is called s orbital. When n is equals to 2, what will be the value of L? 2 minus 1 is equals to 1. And what will be the possible magnetic quantum numbers? It will be plus 1, 0 and minus 3. So there will be 3 possibilities. And the number of orbitals is 3. That is p orbital, and it has orientations like px, py and pz. Similarly for L, if the azimuthal quantum number is equals to 2 and L is equals to 3, the number of orbitals will be 5 and 7, as we saw in this picture. For d orbital it is 5 and for f orbital it is 7.